Good.
Thank you. So the function here is x squared. This is the parabola, our friend. And the question is asking for finding the right endpoint and left endpoint value of this guy. Sorry, right endpoint and left endpoint approximation of the area under the graph of x squared on the interval 1 and 2. Yes, so we have the function x squared, the interval 1, 2. So remember, this is a, this is b. So a is equal to 1, b is equal to 2. Right away, you can see that the length of subintervals that we will use is going to be 2 minus 1, right endpoint minus left endpoint, divided by n. So 1 over n. Left endpoint xi is always a plus a right endpoint, sorry, is a plus I delta x. In other words, xi is going to be a is 1 plus I times delta x is this guy. Left endpoint is xi minus 1, which you can see in general is a plus I minus 1 times delta x. And in this case, it's 1 plus I minus 1 times 1 over n. Now, if you're looking for the right approximation, is the formula is sum of delta x f of a plus I delta x, and I goes from 1 to n. And you can see that this guy here is sum of 1 over n. I goes from 1 to n. F of 1, oh, I already have it here. 1 plus I over n, and f of that is 1 plus I over n squared. That's our function. Here, this 1 over n is a constant, and I can take a constant multiple outside of the sigma. And this part I can expand 1 plus 2I over n plus I squared n squared. Now I can separate these cases, sigma 1 over n, sigma of 1 plus 2 over n is that constant, and we go from 1 to n plus 1 over n squared times sums of I squareds. I goes from 1 to n. Very nice. So sums of 1 is n. If I goes from 1 to n is n. So this is 1 over n times n plus. Let me find one by one. Sums of i's, I goes from 1 to n is n times n plus 1 over 2. And sums of I squared is n plus 1, 2n plus 1 over 6. And then I have this big bracket. Now I can multiply this inside, and what I will get, 1 over n times 1 is 1 plus. This guy cancels with that, that guy cancels with that. I will get n plus 1 over n there, plus. Okay, so I have some cancellation here. This cancels with that. And then the final is what? N plus 1 times 2n plus 1 over 6. There's 1n here, there's 1n here. This is 6n squared. And well, then you can simplify that. So it's 1 plus n plus 1 over n. Let me just expand the numerator. This is 2n squared plus what? 3n. And then plus 1 over 6n squared. We found a formula for Rn. And that works for every n. For example, if someone says approximate the area under the graph of x squared when you chop it into 100, that means that you have 1 plus 100 plus 1 over 100 plus 2 times 100 squared, which is 10,000, plus 3 times 100 plus 1 over 6 times 100 squared, which is 60,000. And for any number of n that you want to chop the interval into subintervals, you can use that formula and find that that Rn. Well, similar computations will work for the Ln. I won't do that. I'll just write the first steps. This is 1 over n, 1 plus I minus 1 over n squared. And then if you try to do these things, you will find a formula for Ln. And obviously, the right and left endpoint approximations for the equal number of subintervals are going to be different. They are going to be completely different things. But the important thing is that when you find limit of Rn or limit of Ln, since x squared is continuous function, these guys are going to be equal thing. And that limit is going to be area under the graph of x squared on interval 1, 2. And if you're interested in, well, I can use limit of Rn, which is n goes to infinity. Here, well, you either replace n by x, and then you see that infinity over infinity, you can use L'Hopital rule, or you just factor out for each part, so separate these pieces. For each part, you factor out the highest power in the numerator and denominator, and the limits you will find will be 1 plus 1 plus 2 over 6. So that will be 2 plus 1 over 3, which is 7 over 3. If you find Ln, please do it yourself. If you find Ln, you will notice that, well, Ln is different, but the limit will be exact same value there.